Hey, folks, and folks hear me. Thank you for letting me know. Tell you, let me fix it here. How about now? A little easier? Let's see if we can fix that. Give me a second here. We don't want that. Don't want an echo. We got an echo in one of the things. I don't know if we're getting that on YouTube as well. Not sure what changed. Wasn't getting that this morning, I don't think. I know what happened. Give me a second here. I think I figured it out. All right. Now it's a different wrong screen, but can you hear me now? You kidding me? Stream, just be patient. We'll fix this one step at a time. Oh, I know what happened. All right. Now, how about now? Yeah, on Zoom has a setting where, okay, look, I won't bore you with the details, but it was one of many settings that decided to revert. Anyway, hope all can hear me now over Zoom without echo. It's good to have you. Thank you for your patience. Also, the reason we have an echo is I think I've fixed something with the Zoom side of this. So, like for instance, if I pull up right now the screen here, I don't know if you can see this a little more crisply. Can you read what I'm writing here? How's that for looking here? Can you read that? Or you need it a little bigger. Great. Oh, you won't believe what I had to do to make this happen, but it works. So it's good. I'm glad. So anyway, great. So anyway, so hello friends. It's good to have you back. So today, we're doing a little bit of a coding lecture. Please remember to get in your project groups. There should be your project group submission form should be available on Canvas. Okay. Yes, looks nice. It's so clear. I'm so happy. You can see the screen much more nicely through your Zoom. Oh my gosh, I won't tell you. Anyway, I'm just so thrilled. Good to be thrilled to be here with you all, particularly because I'm here to talk about coding up neural networks, sort of the backbone of modern AI. And we're going to do it from scratch today. Is it going to do much? No. But I want to show you how it is not that huge of a deal. But anyway, so we'll get started today. But again, remember to get your project groups in, and when you have those submitted, start thinking about your projects themselves. We're gonna get out this official sheet soon. That's on me, and we'll get that out. But get your project groups together, but yeah, I'm just super excited for today. So maybe I'm a little frazzled over the excitement that we get to code up a neural network. Okay, so let me start off today for our lecture. So we've got, today we're going to be coding neural networks from scratch. All right. Because to date, all of our models have been these linear models. Even when they draw more than just lines, even when they're regressions with polynomials, we can do linear regressions to fit them. But a incredibly powerful model, as we talked about, is the artificial neural network. Now, just for the sake of argument, just so it's clear what we're talking about artificial. Start recording. So we're going to be coding up artificial neural networks today. Artificial. Often called ANNs or just NNs. Here. Most people just assume the network is artificial because you're not growing it out of rat neurons or things like that. That's a different field. We won't be covering that here. So, but previously, our models have been linear. Okay, they are very easy to fit, but not as flexible as we sometimes need. Reset this here. Excuse me. This is a backache waiting to happen here. Go. Sometimes need. Okay. So the idea that you have a model that we want to take some particular shape, here's some input, and here's our output of that model, y of x. If it's a function, it would be great if we could make it make any kind of functional form that we want, right? Anything we want. That'd be incredibly powerful. And neural networks, artificial neural networks, offer us that capacity. And we have been building toward the neural network, including how we might take a derivative of one as of last week. We have not coded one yet. Okay? So an artificial neural network is a computational graph where operations and activation functions are connected by weighted edges. You can come up with lots of different definitions, but this is a pretty good and general one. It's a computational graph, meaning it's a graph in the sense that we talked about last time, or in the sense of mathematics, where you have edges, which are lines, and vertices, which are like little connecting points or nodes, okay? So it might look something like this. We will be dealing with directed graphs. It might look something like this, where you have here might be an input. Here would be an output, as an example. And here might be functions. Which have different inputs. And along here might be weights. Wi, Wj. And these weights are things that multiply signals. Okay. Weights are connections which multiply signals. Okay? You can call them WI. Odds are you're going to have a multi-dimensional set of weights, meaning that like might just not just be a list of weights, it might be a matrix of weights or a tensor of weights, if you will, a multi-dimensional matrix with, that's not just 2 dimensions like a square, like a rectangle, but instead comes out into space, called a tensor, or more generally is called a tensor. So are the functions the middle circles? Yes. Functions are the middle circles. Let me put that as a little bit of a different color to make that a little more clear. Functions here, right? Those are our functions. Awesome. Cool. Nifty. Cool. So, excuse me. So, and you can design this graph in any way you want. In fact, there are sometimes graphs that will not just go forward in one direction from input to output. You might have connections that go back to here, which then go back to here. They actually loop around, okay? Those are called recurrent neural networks. Today, we're going to be dealing with what we call a feed-forward neural network that just goes in one direction. You have an input that goes in here. There are weights and then computations, and then these values come out of the functions and they get weighted again, and they get operated on here. Typically, they are summed back together, and they're an output. Okay, so these neural networks that we're talking about are not the math that we're talking about is no more sophisticated than the math that you'll get on a typical scientific calculator. Science fiction calculator. It's a different thing. Okay, now in a neural network, these functions, we will call them activation functions. So activation functions let's call them h of x. There are people sometimes call them a of x for activation. Today we'll just call them h of x. All right. Are scalar valued functions that represent activation of a neuron when a threshold is reached. Okay. The idea being, here's your activation function, here's your input x, here's h of x. Here's an example of what it might look like. Let's say you have a function that activates here at that value of x. It might look something like this, where it is where it is 1 when it's activated, and 0 when it's off. That's an example. It doesn't need to be 1 and 0. Sometimes it's 1 and -1. It's all kinds of things, right? But the idea is that here, it activated, right? Again, this is analogous to neurons in the brain or in the body, that when one neuron fires, if it fires strongly enough, then the one next to it will fire, and then that one will fire, then another one will fire, and it creates these neural firings in your brain. It's analogous to that, right? So if you have a network of them, you can get to do all kinds of crazy computations. All right? Middle circles are functions. All right. So you have a neural network. It's a computational graph, so you'll have some kind of numbers going in and then functions. Then they'll be multiplied by weights. They'll go into activation functions, then they'll go into weights. It might go into more activation functions. Again, who gets to design what that looks like? We do. And the more complicated we make it, generally speaking, the more stuff we can get it to do. Remember, we talked about the idea of capacity of a model? The more neurons and weights that you have, the higher capacity your model tends to be. All right. So even if your single activation function is that, it's not that complicated. Let's just this particular curve, this little S-shaped curve. Excuse me. Even if that's not that complicated, if you connect it where the output of this little neuron, in fact, I'm going to draw a little S shape in here, if that's okay. Woo, a little S like that. Even if the output of this one neuron is simple, if the output of that got fed into another neuron, it'll get warped again by a similar looking shape. Okay, you do it enough times, you can get it to make all kinds of these crazy shapes, like I'm showing back up above, right? And I'm just showing you, by the way, to be clear, a single X value input. And therefore, this output I'm drawing of Y of X with X going in is just a line in this little function space, right? There is nothing stopping me from having multiple X's and making X a vector with many values, right? I could have two of them, and at which point I could make this all look like a surface. Here's Y of X1 and X2, and here's X1 and X2. That's a weird looking. So I'm trying to draw the grid of a surface that's kind of wacky and wavy, right? See that? And doesn't need to stop there. That's a 2-dimensional input. It could be a 10-dimensional input, at which point I'm looking at a little 11-dimensional space. Okay? Not crazy. So and so I mean it's crazy, but like it's to the math here, it's just more numbers in a vector. It could be 1,000 inputs, so for all you want. You can have multiple of these outputs too. There's nothing stopping you from having multiple outputs come out of your function, right? They can go out to here as well. Okay. So what we're going to talk about now is a perceptron, okay, is an artificial neuron designed to represent an activated signal. Okay? And what we're going to be talking about is what we call a multi-layer perceptron. So I'm going to show you a multi-layer perceptron called MLP. This is what we're going to work toward building. Okay? The idea is you have some certain number of inputs. Okay? X bar. These are inputs. You can have more than 2. Right now I'm just drawing it with 2. Then I'm going to draw these little activation functions with little S's inside. Okay? And each of these inputs are connected to these little activation functions. Every single one of them. That should be 8 of them. Hopefully I drew. Yes, I did. Okay? And with every one of those connections is a weight. Okay? And so we'll call it weight I, comma, yeah, we'll call it weight, just W. Okay? Lowercase w. Right now there are 8 weights as I've drawn here because there's 2 inputs. And you have these activations, right? So, and then let's draw another layer of these weights. It doesn't need to have the same number as the previous layer, but sometimes it's just convenient to do that. And we're connecting every combination from one layer to the next. And then we'll stop adding more layers. We'll just have what we call our outputs. Okay. And these outputs, we'll put a little sum in there, a little sigma. So we'll add them up. Okay. Shoot. Okay. These will be our outputs. These are called the input layer. These are called the output layer. Okay. You can have different, and in the middle here, we call these are called the hidden layers. Right now we have 2 hidden layers. These are 2 hidden layers there. That's a layer, that's a layer. Okay, you could have 1 hidden layer if you want. You know, you could have 3. Okay. This is a multi-layer perceptron. Okay, it's got layers of them. And we would call this a feed forward. A feed forward neural net. Okay. The feed forward neural network, because it only goes in direction, it only goes in one direction. Okay, there are no loops. These signals do not loop. You can see what's called the recurrent. They do loop. Okay, we're dealing with just feed forward neural network straight through. Okay, and there are lots of ways to set this up. You could have different types of functions in these little circles here. Okay, you could sum them up together at the end, or you could not sum them, or you could just put another activation at the end. Okay, but this will be the output at the end. Here's the input, and we'll say that these are Y. Okay, so, but in general, each of these functions will take in the sum as an input, the sum of all of its inputs multiplied by different weights. And all of the learning in this particular context for a multi-layer perceptron, when we talk about learning, try to learn a model, we are learning all these weights. Every single one of these lines has a different weight. As you can see, there'll be many of them, right? As you'll see very shortly, you can't just do linear regression on them because these are very much nonlinear functions. We'll have to do gradient descent. All right. Okay. Any questions so far? Is this making some sense? Any questions about this? At least just a high level. You have a number that goes in. That number, maybe I'll walk you through it a little bit, okay? So let's say you put in a number, and let's assume we have some weights that we have for every single one of these lines. How they were chosen, I don't care at the moment. We'll get to that later. Let's put in a number into this. That's our input. And the idea is to figure out what are our outputs. Let's actually execute this multi-layer perceptron. We'll call that inferencing. That's a different story. But anyway, let's actually execute it. So we would put in a number here and here. Then we would take that number, multiply it by this weight, then take this number multiplied by this weight, add them together, and they are the input to this activation function. Then The output of this activation function is multiplied by this weight, goes to here, plus the output multiplied by this weight goes to here, plus the output multiplied by this weight, and this weight. Cool. Now, in order to compute these activation functions, we have all those other lines that go into them. So we have to go back to here or here. And then multiply by that weight, goes into there, goes into there. We have to evaluate all of these functions. And that gives us all the information to then multiply by the outputs that go into all of those. And then they get activated. And then the outputs go to there. And they're all summed together and they give you your output. And you can make any kind of shape that you want. And that shape is power. I understand it's a little abstract right now, but that's how you get it to say, hey, that's a cat. Versus that's a picture of a dog. Where all of these inputs might be the color values of an image. It's a little more complicated than that. You want to use a different sort of kind of network, but there could be some network in the middle here that takes in all those pixel values. Like, oh, it's 255 red for RGB, 100 green, and then 50 for blue for that pixel. Then all these other pixels, those are your inputs, and the output is dog or cat. So then the crazy shape is power. All right. So the output of a given activation function y is going to be equal to h, so which is your activation function, of w, which is all your weights in a vector, transposed times x plus b. Okay. This is your weight vector. That of all the weights that are tied to the input of a function. And this is called your bias. Meaning it's just a number that's added on top. Okay. And that bias can also be adjusted as part of the optimization. Now, in practice, we have a way of doing that without adding an extra b term. What we do is we add another input where the input is 1 and it's multiplied by another weight, w. And so that b is just 1 times a w. So it's just another weight to optimize. So a weight and a bias. So to just demonstrate how this whole weights and bias things works on a neural net, let's code up a very simple, code a single neuron where our activation function, where h of x is the hyperbolic tangent tan h or tanch. All right. And if you don't remember what that is, which I don't blame you. I mean, who's used hyperbolic tangent recently in their lives? Anybody? I'm just curious. It's not a shame factor. It's not everyone uses it. Everybody? Nobody? See, actually, I don't have the participant screen up to see. Yeah, nobody, it seems. That's okay. Hyperbolic functions are also how you can determine, like, if you have a cable that's being routed via telephone poles, the shape of that cable is dictated by hyperbolic functions. But mathematically, if you wanted to write it out with more simple functions, it is e to the x minus e to the x over e to the x plus e to the x. Oh, sorry, e to the minus x. Sorry, minus x minus x. E to the x minus e to the minus x, e to the x plus e to the minus x. All right. And why do we like this? And if you're curious, like, the reason they call it tangent is because it's actually equal to the equivalent of the hyperbolic sine of x over the hyperbolic cosine of x. So literally, like, tangent is sine over cosine. Same with the hyperbolic functions. Just a reminder if you haven't seen it in a while. Okay. The reason we like it is because here's the shape of x versus tangent of x. Here is the number 1. Here is the number -1. And it looks kind of like this. Right? So that looks like an activation function. Down here, beneath some threshold, it is off. Up here, above a certain threshold, it's on. As it gets closer to 1, it's on. As it gets closer to -1, it's off. That's -1. So let's code a single neuron in Python. So just open up Google Colab, colab.research.google.com. We're going to make a quick neuron. All right, let's pull it up. So here I've got Google Colab. We'll make it a little bit bigger, my friends. All right. So I just made a new notebook. Okay. And I'm going to put a little text here. And I'm going to call it, neuron. We'll call it first neuron. Okay. We're making a neuron. So we are coding a neural network from scratch. From scratch. Okay, so we're going to start with our libraries that we need, our Python libraries. The ones we're going to need are NumPy to do all of our math. So we're going to say import NumPy. We're going to alias it as NP. We're going to import our plotting library. We definitely want to plot. We're going to import matplotlib as .pyplot as PLT. Okay. And we're going to run that. Now we have that code block in there. Okay. So now I'm going to, we're going to create a single neuron with a tanh activation function. Okay. So with our tanh activation function, so what we're going to need to be able to do is I want to plot this. I want to plot this activation function right here. So I want to plot it. I'm going to want to plot it over a whole bunch of different x's along the x-axis. So I'm going to make a whole bunch of x's in a vector. And I'm going to do that using the linspace command. So x equals np.linspace, which creates a whole bunch of linearly spaced elements in an array. I want to go from -3 to 3, and I just want 1,000 points. So I have a nice smooth curve to plot because I can. So if I wanted to then plot, I can plt.plot. I want to plot x versus the tanh of x, and now the tanh of x is actually in the NumPy library, so we have to say tan np.tanh of x, and let's just make it a black line for now. And let's say plt.show to show our plot. Let's run everything for good measure. Hey, look, there's our little tanh. Look at that. Off, it's down by -1, and on, right? That's just tanh. Okay, so it looks like a little neuron, right? So, however, we also have the fact that the activation y is also dependent on these weights and these biases. Now, we only have, if I were to draw this neuron, here's my activation function. And in goes x, out comes y. Sorry, I guess I should say here is x, and here is y. Okay? And along the way, there is some weight, w, only a single weight. Okay? You don't have to worry about a single number, and there's going to be a bias that is added in, just a single value of b. Okay? So literally, our activation is going to look like y is equal to h of w times x plus b. And we will just arbitrarily choose these weights and these biases, okay? A few things I want to do with the code. I want to set the axes. So one thing you can do to set axes, there are a couple ways to do it. The way I'm going to do it today is I'm going to grab the axes as an object, as a thing that I can change. I can say ax is equal to plt.getCurrentAxes, open close. When I run that command within this little object called ax, I can now change elements of the axis using all the functions within the axis. So I could say ax dot set underscore xlim, and set the x limits. I want to set the x limits to be -3 and 3. I'm going to set my y limits. I'm going to make them positive and -2. So I can say ax dot set ylim -2 and +2. And if I run that, there we go. I have set my axes a little better, right? I just in a way that's constant. No matter what I do change of the plot, those will be the axes. Okay. So I also have these weights and biases. So I can say, go up here, I can say I'm going to set my weight, and so I'm going to say W right now equals 1. I'm going to set my bias, B. I'm going to set it equal to 0, which means it will change nothing. And instead of just plotting np.tanhx, I'm going to evaluate my neuron in another line of code. I'm going to say that y is equal to np.tanh, because tanh is part of the NumPy package, of w times x plus b. This exact thing right there. It's and where my function is the tanh right there. Okay. All right. So if I run that, it should be no different because my weight is 1. So I multiply 1 by x plus 0, right? If I then multiply w by a value, let's say if I start multiplying by a large number, a large positive number, what's going to happen to this signal? Larger than 1. And without putting it in, anyone want to guess? What's going to happen to it if my weight is larger than 1? Yeah, it's going to get pinched in. It's going to become sharper, okay? So imagine, my friends, exactly. Thank you, sir. So imagine if I wanted a function that was really a lot like it was off, and then it snaps on, okay? I would want to pinch this function together. So multiplying by w, being a large number, let's make it 3. I'm going to run it all again. Yes. What happened? Yeah, I forgot y. You changed it to y right there. Yeah, you're a second ahead of me. I would have realized my mistake eventually, but thank you. Change this to y. Thank you. And look, I changed it, multiplied by 3. Look, it's sharper, right? I can make it a lot sharper. I can make it 30. Look how sharp it gets, right? So the weight changes how important that this number is. It can then all of a sudden sharpen and move to another direction, right? Okay. I'll try what if I do -3? What happens with -3? Oh, it's the opposite. It's on when it's a low number and off when it's a high number. Okay. Now the bias. Now the bias is inside the function, as you might recall from algebra. If your bias is if you add a number to the inside of a function, that's going to shift it to the left or right. So if I add a value that's positive, it's actually going to shift my function to the left. So if I add 1 to my bias, it's going to shift everything to the left. Or did I do it? Sure. Thank you. Yep, you got it. Okay. Made the code bigger for you. So this one moved it to the right, probably because of the negative number. Let me get rid of let's make it a +3 again. My bias is 0. I'm going to run this piece of code again. So this is where I have my sharp function. Now I'm going to change my bias to 1. And it moved it to the left. Okay. So so the bias shifts the activation to the left or right. Okay. So what you could make, so imagine we had a task for this neural network, and its job was to take in a number, and it tells you, is this number above 3, above 2, or below 2? If it's below 2, I want it to spit out a negative number. If it's above 2, I want you to spit out a positive number. Okay? Well, I know just with my own internal brain that if I set my bias to -2, and I'm going to set my weight to a big number, let's just say 50. Here's my neural net. Okay, so did I screw that up? Oh no, I did. I see. I have to do it like minus 100, I believe that's what it is. Okay. All right. I know, just because I have a brain, I know how to set up that function. So hey, the input to my function, if it's less than 2, if it's less than 2, if it's less than 2, it's off. Then shoot, it's on. Great. It classifies a number as being greater than or less than 2. We made a classifier, right? You could have just done that with one line of code, of course, with a greater than or equal to sign, but this is a classifying neural network. Okay, it classified it as being greater than 2 or less than 2. But that's just one neuron, right? And we can also, on the output, throw, if we wanted to, put on another weight, a completely different weight. I'll call this WI and then WJ, just so they're different weights, okay? And so which would multiply my output again. And I can have another bias as well that goes into the activation of my Y, okay? All right. So with each of these neurons, we have weights coming in and a bias. Now, let's add some let's add some more inputs, okay? Let's just have, here's another example. Let's go back to the board. An example. We have multiple inputs. I don't know how useful of a neural network this is, but this is just something so we build it up. Where we have multiple inputs on the input layer. We have a single tanh in the middle that takes in all of these directional edges, okay? And out comes just 1. So we've got, call this W1, W2, and W3. And we'll call that W4. It's not very systematic, but we're just labeling these things. So these are inputs, X bar, and there's our output, Y bar, even though there's only one value, okay? This would be X1, X2, and X3, okay? So if we wanted to get the output of this function, so we'd say H is going to be the output here is going to be W, where W is going to be the input's going to be W1, W2, W3, transpose X, where X is going to be our vector of X1, X2, and X3, plus some bias. That's what's going to come out of that neuron, which can then be multiplied by a weight and become some output. Okay? Now, why do we write it in this way? Well, if you work out the linear algebra, this is the same as saying the transpose of W, which is W1, W2, W3, which is going to be W1, W2, W3 as a row vector, times X1, X2, X3 as a column vector, plus some bias B. And if you do your matrix multiplication correctly, the result of this multiplication of this vector times this vector, this is a 1 by 3, this is a 3 by 1. You can multiply them, that's all good. So the result is a 1 by 1, which is good because we're adding it to the number B, which is a 1 by 1, just a bias, a single number. Okay? And so the result of that is going to be W1 times X1 plus W2 times X2 plus W3 times X3 plus our bias. And it all goes into that function, which is a tan H in our case, right? So that is how you would set up multiple inputs into our very small typo where you have written W1, W2, W3. Oh, thank you. I appreciate that. I see it. W3. Appreciate that. Thanks, Nick. Right. All right. So that's how you would take the input. Those are the inputs of the neuron. How will we write that in code? Well, let's have multiple inputs. Right now we have W as just a number 30. Okay. Okay. Let's make it an array, a NumPy array. So np.array. Okay. We're going to make it going to have a 1. So we have 3 inputs. I don't know. We'll call them 5, 4, 3. Okay. Well, those are our weights. I'm sorry. These are our weights, not our inputs. They're W's, right? These are weights. Well, 5, 4, and 3 is fine. Okay. And our inputs, the problem is now our inputs are now kind of like 3-dimensional. So right now we have to get rid of this. And so actually, here's what we're going to do. We're going to make a whole new, we're going to undo this. We're going to make it a whole new, undo the change. The weight is just back to 50. We're going to make a whole new code block. I think we can do that. So let's make a multi-input neural network. Okay. Where now X is going to be just a vector of inputs, so it's going to be np.array. So 1.2.3. Let's run it and show what happened. And let's just print X just so you can see what actually was printed out as a debug. This is a row vector. Be nice if it was a column vector. So let's see if we can make it a column vector by saying dot transpose. Nope. Capital T will do it. Thank you very much. I'm blanking. Thank you. Let's print, what is it, the size? Or it's like x.size. Oh my goodness, I am blanking. Okay, not callable. Anyway, do that with a second, all right? Yeah, Nick, if you could pop in some syntax into the chat, that would be helpful. I'm just trying to make a column vector here, and I'm blanking. So anyway, so we have our input, and we're gonna need our weights. So we're gonna have our weights. Right now, we'll just set our weights to be 1, 1, and 1. We have 3 weights, okay, for our network. And let's set our bias equal to 1. All right. So what we're gonna want to do is multiply. You say that y is going to be np.tanh of w.transpose times x. Okay, I'm going to screw up the, let me print out the result of this real quick, just because I am making some mistakes. W.transpose times x. What happens there? 1, 2, 3. Is that right? Just debugging real quick because I'm making mistakes. I don't want that. I want to transpose. Okay. All right. So one thing you can do is, so you're just doing a reshape here, Nick. So here's you can do a transpose. There's got to be a better way. Okay, but we'll do, in order to transpose, we'll do a reshape. 1 times 1. There's got to be a different way to do a transpose, and I'm embarrassed that I'm blanking on it at the moment. That's how we can do a transpose here. All right. And yeah, np.transpose. Thank you. That's what I thought. np.transpose x. Oh, just give me a second here as I'm reminding myself of the linear algebra syntax after coming out of MATLAB here. All right. So get rid of this. I'm just debugging real quick, so I'll explain it once I make sure it's all working okay. Okay. W.transpose -1 print x. Okay, yeah, we'll do it that way. Just for now, we're just doing, thanks for following along. I'm just real quick, I'm just making sure I'm doing things right here. Why am I getting an outer product then, Nick? If that works that way. So, but the idea is, so I'm working out my MATLAB syntax. X.shape. Three by one, and then W.shape. 3 by 1. Why is it not transposing then? Not .t. So it's probably because I don't have the linear algebra package installed. Is that what's going on? So I want to print x.transpose times w.transpose of x. I apologize, friends. I'll get this working. That's not right. Is that not the matrix multiplication? np.matmult. Nick, could you put the syntax in the chat here? Just want to get that matrix multiplication working. Yeah, I know it's the at, but it's all right. W.transpose. There we go. Finally. Okay. There we go. Now we're in business here. Just it's a couple of syntaxes I was screwing up. So let me go back, friends. Thanks for your patience with all that. So what I wanted to make is a column vector, which you can do a couple different ways. If I were to say print np.array, and I want to make a 1, 2, 3. That should work as well. Oh, and I need a thing here. Okay, anyway. I'm gonna stop improvising for the moment. So I wanted to make a column vector, and I defined it as 1, 2, 3. That's a row, right? In order to turn that into a column, you have to do what? You got to transpose it. Here's one way. Jacob, I can't see that. If you're gonna have to send that to me over Zoom. You can reshape it into a transpose like this, okay? In order to become a column. So this is now effectively W transpose X. Okay, pause for a second here. Yeah. Here we go. All right. np.t, np.t, np. So this is the same as .t. Let's make this simpler if we can. .t. If this works, I'm trying to make this as simple as possible. There we go. Finally. Thank you. Thank you, Jack. blanking on the syntax, jumping back and forth from MATLAB. So anyway, here we got x.np.array.t. This is our transpose. Fantastic. So here we go. Thanks, friends. So this is a column vector with made using a transpose. Okay. Then we've got another column vector made using a transpose, right? Because we defined it as a row, transpose it to column with dot t. Then we want to do a matrix multiplication using the at symbol. Okay, so the result of this is actually correct. This is going to be W1 times x. So it's going to be 1 times 1 plus 2 times 1 plus 3 times 1 plus 0 is going to be 6. Okay, well, if we add the bias in. We didn't add the bias in yet. Where's the bias? We didn't. So, okay, good. All right, finally. Silly little linear algebra syntax for how we do it with Python. But look, that's nice and convenient now that we got it like that. So now if we want to actually make y, so we have so if we want to say have a bias of 1, okay, then the output y is going to be our activation function, np.array. Question? Nicholas, do you have a question? Okay. Cool. Then you've got w.transpose times x plus b. All right, that's the y, that's the output. Then if we want to plot it, then we can say plt.plot. We want to, oh, actually, we're not plotting anything because we're printing the output. Printing the output y. And then I forgot the at symbol. That's why. Boom. The at symbol. 7. Okay. So the at symbol is the matrix multiplication. Okay. There we go. So that's how we can make a multi-input, single output neuron. Okay. Now, what do we do if we have multiple neurons? Okay. You could have, and how do you get the output of them? So let's go back to our board. So let's say we have 2 inputs, or maybe we'll just do, I don't know, let's do 1 input with multiple neurons. 4 neurons. We do need multiple inputs. Yes, here's what we're going to do. We're going to make a multi-layer perceptron with multiple layers here and connect them all. But now all of a sudden, our biases become more complicated. Yes, there's only 4 biases here, plus a bias, sorry, 4 weights here, 4 weights here, and then also 4 biases. So now we need a bias for every single one of these neurons, different for all of them. Okay. Right? And there's a real easy way that we like to incorporate that. Here, this is an input, we'll call that x. Instead of having an individual bias variable for each of these neurons, what we do is we add an additional input. This is a trick you can do. You don't have to do. The input is just the number 1. That's just 1.0 right there. And what you do is you then connect that input with its own weights to each of the inputs of the next layer. Okay? And you can do the same thing here. You have another bias here with just the number 1, and you connect it with its own weights to the layer. So then those weights times the number 1 become the bias. So now we have here 2 inputs. And then we have 4 neurons. That means we're going to have 8 of these connections, right? So we might have, one way to represent that is all those weights would be a 2 by 4 matrix, where each row represents the connection for one of the inputs. The first one is X, and then the second one is just the number 1. And the column corresponds to which neuron they're multiplied by. Okay? You can do it either way. So you can have a, so that would mean that if we have 2 inputs, let's just say our inputs are X and the number 1, that's a 2 by 1. And here we have W transpose, which W is a 2 by 4. You transpose it, it becomes a 4 by 2, right? This multiplication does work, and it becomes a 4 by 1. Okay? So the result of this matrix multiplication is equal to a 4 by 1. And those are all the numbers that will go into our function. We go into our activation function. Okay. So great. So that means that the output we'll call of these functions. What's the output of all these things here that come out of each of those neurons? Let's call that y hat. That y hat is going to be equal to our activation function h times, again, W transpose X, but the biases are already included into this input vector, which now has the number 1 in it. Okay? So that means that if we wanted to, so let's make another neural network in our code. Let's go to the code again. Okay, let's make another neural network. Say we're going to be making a multi-layer perceptron. We're going to make it with 1 input and 1 bias. 4 neurons in the first hidden layer. Okay. So right now, let's say just our input X is just the number 5. Okay. Later, we can actually loop this and show what the output of the network is. Let's just wait for that though. Okay. And our bias is just the number 1 for the moment. No, it was yeah, the bias has what goes in is that B, that's that number 1, right? So we're going to create a X input layer. So it's going to be np.array, and we got, and it's going to include just X and B, and we're going to learn from our mistakes and transpose it like that. So if I print xi on the next layer, there we go. Did I do that right? I swear, if I did it wrong again, I think it's just not printing correct. I think it's not printing a column. I think it's what's happening. All right, so that's xi. Now we need to have our weights. Okay, now our weights, as we determined, is a 2 by 4 matrix. Right now, let's just fill it with just numbers like the number 1. So W is going to equal to np.array. And it's going to have 2 columns. So the first column, the way we'll say it's 1, 1, sorry, the first row, 1, 1, 1, 1. These 4 are in the first row. And then in the next row, we want 1, 1, 1, 1. Okay, this is our weight matrix for the first layer. Okay. Let me print W just to show what it looks like. These are good debug practices, so you can see, hey, look, it is a 2x4 matrix filled with ones. Okay, there are easier ways to fill a matrix 2x1 with ones using the ones command, but that's not what we're doing here. Okay, all right, so so that works. Now we don't need that debug statement anymore, I don't think. So now, but the output, we'll call it y, is going to be equal to the activation function tanh operated on w dot transpose at x. Okay. And let's see. And if I do that right, that should just be that should be 4 numbers that come out. To be because it's a 4x1 as we see right there. Okay. So if we then print the result of y, see what comes out. Oh no, it didn't like that. Oh, xi. That should be xi. Apologies. Here. Great. It gave us 4 numbers. What do they mean? Nothing much yet. Okay. But this is the output of this layer. This is what's coming out here. And then before it comes out to these nodes here. Okay. Before to this layer. And then we're going to have that layer come out to a single number. That's what we'll do. Have a single number with all these weights just summed together. Okay. So, all right. Now we've got, this is the output of the first hidden layer. Okay. Now the output, yeah, question, what you got? You're getting sixes instead of that 0.9. What will be different? Did you remember to do the tanh of it? You got it. Sometimes I have my moments. All right. So, someone got an error. What does the error say? You got an error for them. 2 minus 3 minus tuple has got 1. I'll tell you what, why don't I just copy this into the chat and see if you see anything different when you plug that into your code, okay? While you look for any differences. I can't quite identify what that difference is based on what you described off the top of my head. Give that a shot, see what you come up with, okay? All right, so that's the output of the first hidden layer. Now we want to do the second hidden layer. So right now, this is weights. We want to do another matrix of weights. So I'll call this matrix weight 1. And I'll change this one to weight 1. All right. Now we need more weights. How many weights do we need? Well, I see 4 inputs and 4 outputs. That's going to be 4x4. So we have 4x4 weight matrix for our second weight matrix, right? Okay. And now we will just populate this, or try to populate this with a bunch of number 1s. So np.ones, and I believe we can just do, what do you say, 4x4. Let me just print W2, make sure I remember the syntax. There we go. I got the syntax right. There we go. This just creates a weighting matrix, a second weighting matrix that represents all of these weights right here. Okay? And I'm populating it with the number 1 with the ones command. It's a 4x4. Okay. And I need one for the bias. Oh, Cricket, you're right. Oh. We need a 5th one, don't we, friends? Why? I forgot this. We need a 5th one for the bias. Oh, I'm so stupid. So it's a 5x4. Okay? Full of 1s. Thank you, Cricket. Right? We got one for the bias. We need that there. So now let's create the output of this layer. Let's call that one Z. Okay? That's Z. So Z is going to be very similar to how we set up the Y line, where instead we're going to say that Z is equal to np.tanh, which is our activation function, of W2 dot transpose matrix multiplied, which is the at symbol, times y. Okay, but the only thing is we also need to include on top of y, we need that additional 1. So we got to append 1 onto the end of it. I'm actually, let's see, we're going to say that y, I need to append a 1 on the end because you need that y, and just like we added 1 on the end of x, okay, we need to add that 1 there on the end of y. So let's try out how to do that. Real quick, I'm just going to see if I can do that with a command here. Let's see. What if I say print np.append on y, just the number 1? What happens? Oh, it just puts it on the end there. I don't like that. Wait. It is right. Hey, I did it. There we go. Let's get rid of that thing. Look how smart we are. We appended on the end of y a 1. So all we need to do is say, hey, our new y, my friends, is equal to np.append. It adds an extra number onto the end, and it's the number 1. Oh, look how smart we are. Okay, so now if we do z w2 times y, and let's print z, that should hopefully give us another 4 numbers. Let's see what we get, friends. Indeed we do. Indeed we do. Isn't that nifty? Okay. We need one for the bias. There we go. We got Z. Now we got the Z layer. Done. Now for this last layer, let's just multiply it by, let's just literally, we call this a linear layer, where all it's doing is it's taking all of these W's, multiplying each of these outputs that are now Z, multiplying them by W's and adding them together. Okay? All right, and that'll give us Z, and that'll give us, what do we want to call it, friends? Running out of letters. There's no more Z's. W, X, Y. The X, Y's, and Z's are all taken. I don't know. P for prediction. Call it P. For our output. Sure, why not P? So we got P. We have our output. So our output, P. We're going to need yet another weighting matrix. Call it W3. And it's going to be np.ones. And it's going to be, there are 4 inputs coming into this layer because there are 4 outputs of this layer. But we needed that extra one for the bias, right? As Cricket would point out. Right? So we need 5 of them. But there's only 1 output that it's going to. So it's a 5 by 1. All right, and we'll store it full of 1s. And now our output P is going to be equal to, oh, we have to do the append trick, right? Where we say Z is now equal to np.append. Onto the end of Z, we have to add that number 1 for our biases. And P is now just going to be equal to W3 transpose at Z. And then we're going to print Z, we're going to print P. Shoot, what am I doing? Print P. Get rid of this print Z. Okay, what did I screw up here? Output P. np.ones 5-1. np.append Z. Ah, thank you. Yep, you're right. Because I'm missing parentheses on the MP1s. Just the syntax of this command. The outer parentheses are because it's a function. The inner parentheses are what we create, what we call a tuple or a tuple. Okay, that says I want a 5 by 1. Thank you very much. Boom. Okay, we have an output. All right, that's just a number. Okay, I don't know how exciting that is, but it would be good to actually display an entire curve of a whole bunch of inputs X. Right now we only have 1 input X right here, and we have 1 output P. Perhaps we can just evaluate this in a loop over and over and over again to get a curve across many possible inputs to know what the shape of this neural network is. Okay, so let's see if we can do that. So all of this here, we can, instead of x being 5, we can instead put this in a loop. We can say for x is in range of np.linspace minus 3 to 3 with 1,000. Okay, colon, and I'm going to put little indents here. So basically, I'm going to make x a whole bunch of different values, and we're just going to plot a whole bunch of different points for what x could be, for what the outputs are for all these different x's. Get rid of the print. Okay, and at the end, we're going to say plt.plot. We're going to plot x and p, and it's just going to be a little black, I think a circle. Do a circle for now. And at the end, let's get rid of the indent and say end plot.show. This is not super clean, but what should happen is this should run the loop with different x's, plot a point for each of where the x's show up after the neural network prediction, and then it shows the plot. We'll see if it works. Did not. For x's in range, I need to create an x vector. X vector. I'm going to make that the linspace. I'm sorry, I'm screwing up all my syntax today. I apologize for that. Let's get that working. np.linspace from minus 3 to 3, 1,000. We'll get this working. And what we'll do is we'll say from in range, from 0. That's not the syntax. From 0 to 1,000, and we'll say that x is equal to x underscore vector. X vector, open bracket, and it's not x, it would be I is in range. Ugh, goodness. I knew that x and x vector. Yeah, I'll do the same thing. You're right. Thank you. This is what MATLAB is screwing with me here. Look at that. That's what a neural network looks like. It's not very interesting, but how you make it do more interesting things? You mess with the weights and the biases. And you do that with gradient descent, okay? This is the result of a multi-layer perceptron right here. We just did it in like an hour and a half, okay? All right, and yes, there's a better way to do this. You could say for x is in range, so for x is in np.linspace. This is a much smarter way to do it. Rerun it. Perfect. Oh, wait, did I screw that up? Get rid of that line. There we go. I'll leave that up there. Okay. That's what we got. So, with that, we did it. We did it. We made a multi-layer perceptron. We did it. It doesn't do anything interesting yet, but again, all we need to do is mess around with these weights. W1, W2, and W3. How many are there? There's 5 here, there's 20 here, and there's 8 here. So by my math, that's 33 different weights. How could we optimize that to do what we want? Well, gradient descent. So we have to learn to take the gradient of that neural network, for which we'll need backpropagation. And with that, thanks for going 4 minutes over. You're all released. Thank you for your time. I'll stick around for 2 more questions with the Zoom. And thanks for your patience today. But we did it. We did it.